All right, stats. Welcome to your notes for Tuesday, the 23rd. All right. This is mostly coming from the very end of your chapter 11 notes packet here, which is all about the central limit theorem. We are going to be looking at the very last page in this. There's a 377 at the top right. We're looking at reading rates, gas mileage, and the oil change. All right, so have that right next to you. And we'll finish this up. I've got, I think, a few more questions when I see you again on Monday, the 29th. And we're going to take a class and a half or so to get ready for this quiz, which is going to be on Wednesday, the 1st. All right, so here we are, folks. Here we are. We are in the big stuff of stats here. So this chapter, we got to look at two different equations here. Normal distribution, this is from chapter 3, and this is from chapter 11. This is all about a mean following the normal distribution versus an individual. And now we are going to use both. So on 21, I'm just going to read it. The reading speed of second grade students is approximately normal with a mean of 90 words per minute and a standard deviation of 10 words per minute. What is the probability that a randomly selected student will read more than 95? We're just going to say 95 or more words per minute. All right, we're going to say greater than or equal to 95. Now, this is a single individual, and X is your reading rate, words per minute. X is normal, 90, 10. Okay, I want to see that up top. What is the probability that X is greater than or equal to 95? So my Z score, I'm using equation number 2 here, is 0.5. If you look that up, that's 0.6915. Probability that this person reads at a rate of 95 or more words per minute. So basically a 31% chance. So not terribly unlikely. Okay, almost 1 out of 3 students will do that. Almost 1 out of 3 students will do that. In a classroom of 12, like the next one says, we should expect at least 4 students to do that. In a classroom of 24, we should expect at least 8 of the students to do that. Now, B is asking, what is the probability that a random sample of 12 second grade students has a mean score? So this is overperforming. Puts you in the 70th percentile, the top 30%. That is overperforming. Now, I want a collection of 12 students that as a whole has an average that puts them into the top 30%. So how likely is that? So the probability that X bar is greater than or equal to 95. I'm using equation 1. Z is equal to 95 minus 90 over my standard error, we'll call it later, 10 over root 10. I'm sorry, 10 over root 12. Put that in your calculator and do 5 divided by the answer. I get a Z score here. That's obviously bigger because I'm making the denominator much smaller. 95, 82. So the probability of this happening, 4%. We're getting into outlier area here, okay? This is not likely. If I had 25 second grade classrooms of size 12, one of them would have an average of 95 or more. Okay? Now, it's probability a class of 24. A class of 24 has an average. An average word per minute. Again, this is a random. This is not like we take all the best scores and put them in class. This is a random class. All right, so 95 over 90, and then 10 over root 24. 5 divided by some number. There is 2.45. That's the area that it corresponds with the Z-score. This is a 0.7% chance of happening, like 1 out of 130. If I had 130 truly random second grade classrooms, all size 24, one of them I would expect to have a reading rate of that or higher. Again, this is random. And randomness is very important when we have like studies to show effectiveness of something. All right, so a teacher instituted a new reading program at school, and after 10 weeks in the program, it was found that the mean reading speed of a sample of 20 second grade students was that. What might you conclude? All right, especially if they had a mean of 90, 10, or very close to it, maybe a little bit under it. What could we see? So I do the same thing, like 20 is my number here, 10 over root 20, find that decimal. 2.8 divided by that number is 1.25. So that would happen about one every 10 second grade classrooms of that size. So we can say that, well, she's done something right here. And we wouldn't say like, oh man, no chance of that. Okay, so that that's definitely an impressive result. That's a almost top 10% result. But we wouldn't that would definitely not raise 5, because look, that average is just under 3 words per minute better than the average. Okay, so we wouldn't really bat an eye there. That can definitely happen. There's a 5% chance that the mean reading score of a random sample of 20 second graders will exceed what value? Here, we want this to be on the high end, top 5%. That's the 95th percentile, and that z-score is the exact 1.645. 1.645 is equal to x bar minus 90 over my standard error. Find this decimal, multiply it by 1.645, add 90 to it. 93.68. That is a great question. Next one, we're talking about the Chevy Cobalt. Almost as great as the Chevy Cavalier, which was my first car. Have found, so tests on the Chevy Cobalt have found that the miles per gallon in highway driving are normally distributed with a mean of 32, a standard deviation of 3.5. What is the probability that a randomly selected Chevy Cobalt gets more than 34 miles per gallon on the highway? So X is equal to gas miles per gallon. And X is normal, mean of 32, standard deviation of 3.5. I want to know what's the probability that X is greater than or equal to 34. Again, you're going to have to know when we're dealing with X and then X bar. 34 minus 32 over 3.5 is 0.57. That's the z-score. That z-score corresponds to that area. 1 minus that, 28.43%. That's the probability. All right. So not incredibly unlikely, Out of every 7 Chevy Cobalts we choose, 2 of them will do this on average. So 10 Cobalts are randomly selected, and the miles per gallon for each are recorded. What's the probability that the mean miles for the 10 selected is at 34 or more? So I have 10 in here. I want to know the probability that X bar is greater than or equal to 34. 34 minus 32 over my standard error. So probability is not likely. Not likely. Now, possible if I did this experiment 33 times with 10, one of them would do it. Okay, not impossible. 20 Cobalts are randomly selected, and I want to know the same chance. What's the probability that X bar greater than or equal to 34 with a sample of 20? They want to know, would this be unusual? Yes, it'd be very unusual. 0.5%, 1 out of 200 times this would happen. This would be very unusual. So if they say like, hey, we've found something new we're doing that is increasing, this would be very, very good proof, because this has a 1 out of 200 chance that this would happen without there being some sort of additive, or it would happen on its own. So that's what you're kind of testing in a sample. What's the probability that this would happen given nothing in my experiment going on, like happen on its own? 1 out of 200, not very likely. And that's why I use p-values a lot in these studies, and we'll talk about that and how that corresponds kind of with the z-score when we get to hypothesis testing. Oil change, the shape of a distribution of the time required for an oil change is unknown. It's unknown. So the reason why we were using essential limit theorem before, all those samples were under 30. I told you that 30 is kind of the magic number, and we'll see that later. So that's the answer to A, 30. All right, 30 or more. You'll see why later. So B here, what is the probability a random sample of 40 oil change results in a sample mean of less than 10 minutes? 40 of them, less than 10. So probability that X bar is less than or equal to 10. Negative 2.77 is my z-score. Very, very unlikely. 0.3%. Basically, 1 out of 350 here. Whoa. Not likely. All right. So suppose it doesn't look like they're truly a 10-minute oil change. So suppose the manager agrees to pay each employee a $50 bonus. They meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 a.m. and noon. Treating this as a random sample, what time should they choose so that there's a 10% chance of hitting that time or below? And that's what the manager is going to use. Okay, he's got to make it a top 10% result. Well, top 10 in this case is a shorter time, so you're actually looking for a bottom 10% z-score. You're going to be in the 10th percentile, and that's the z-score that corresponds with it. So negative 1.28 is equal to X bar minus 11.4 all over my standard error. Find this decimal, multiply it by negative 1.28, add 11.4 to it. So 10 minutes and 45 seconds. All right, that concludes the Chapter 11 notes packet, and what I have here is this importance example, and we have one more of these pages when I get back. Then we'll start looking at that quiz review. Important example. So get this page out. We'll do this one, and that'll be it. Suppose that the time needed to produce a single widget is a random variable x with the mean of that and a standard deviation of that. You see nothing about the normal distribution. So if I want to answer questions about the mean time, I need a large sample size, and 50 is greater than or equal to 30. They call a widget anything that you're just a general term for a product. There, you might see a lot of widgets if you're going to business school or whatnot. So, 375. We obviously can't say X bar is equal to 375 minus that over that, okay? Or else you get a z-score of what, 184? No. Could get z-scores close to 12 or close to like negative 8, but definitely not above 100. So what do we have to do here? You got to find X bar. Okay, this is in terms of the total time for 50 widgets. So why don't you just find, and we talked about this yesterday with a similar circumstance in, which one? The airline passengers, 11.34. So I can change this to what's the probability that X bar is greater than or equal to 7.5, because I take 375 and divide it by 50, which I did right here. So what's the probability that X bar is greater than or equal to 7.5? It's a lot closer to 7.3. Z is equal to 7.5 minus 7.3 all over my standard error. 0.7704, I subtract that from 1. What's the probability that those 50 widgets would take less than 350 minutes? So what's the probability that X bar is less than or equal to 7? And I get my z-score. I look this up now. Now take a look at this. So what I was using on what I found online, because I have the z-table right in front of me, and you might take some classes in the future that only give you one side of the z-table, and it's the positive side, most likely. So I looked up 1.12, and that was the area that corresponded with it, so I subtracted it from 1. They would be complements, so that could happen to you in college, all right? You can use it. And what's the probability that it's going to be between the two? That's the same thing as saying what's the probability that X bars between those two values, 7 and 7.5. I take that minus that. That was just an extra. Nope. And what's the probability? One widget. One widget. Well, you know, this is not a good, so let's say assuming, we got to enter this in, assuming approximately normal. Because you can't ask this question unless it's approximately normal. Okay, so put that in there. Assuming that this is approximately normal now, what's the probability one widget will take less than 7 minutes to produce? Right there. Okay, and that is your notes. And we'll review really nice for that quiz. And you guys will also, so start practicing early for that Chapter 11 homework, all right? Get at that early. We are now in the more interesting parts and maybe more challenging part of stats. This is Yak Math Videos, and you guys have a great Thanksgiving break, and we are signing out.